This is the EdExcel AS Level Further Maths Paper 2, covering the Further Pure 1 FP1 module, and it's from the October 2020 series. Question number 1. The variables x and y satisfy the differential equation d squared y over dx squared equals 2y squared minus x minus 1, where dy over dx equals 3 and y equals 0 at x equals 0. And we have to use the approximations for a second order differential equation and a first order differential equation with h equaling 0.1 to find an estimate for the value of y at x equals 0.2. And of course, what you'd notice over here, we have Euler's method to approximating second order differential equations, and here we have the midpoint method to approximating first order differential equations. Now, with these, what we can do is write them in an alternative form. So what you can see then is we can rearrange the midpoint approximation to say we have yn plus 1 is approximately yn minus 1 plus 2h lots of dy over dx n. What we also see is for Euler's approximation for a second order differential equation can be written in this form: yn plus 1 is approximately 2yn minus yn minus 1 plus h squared lots of d squared y over dx squared n. Now if we take a look at the question, we need to find an estimate for the value of y at x equals 0.2. We have already x equals 0, and we have our step length h equals 0.1, and therefore what you can see is we require 2 iterations to find an estimate for the value of y at x equals 0.2. Of course, for the first iteration, we can find the corresponding y value at x equals 0.1, and then of course for the second iteration, we can find the corresponding y value at x equals 0.2. So far we've been given x0 is equal to 0, and at x0 equals 0 we know already y0 is equal to 0, and dy over dx 0, that's equal to 3. And because we know the value of y and the first derivative at x equals 0, we can use this information to find out the value of the second derivative at x equals 0, and to do that we would have to use this differential equation as we see here. So d squared y over dx squared 0, that will be given by 2y0 squared minus x0 minus 1. And using the values we have here, we would have 2 lots of 0 squared minus 0 minus 1. It turns out here we get negative 1. Now let's move on to our first iteration. With our first iteration, bearing in mind that h is equal to 0.1, we can find the value of y1. So, at x1 equaling 0.1, we can find an approximation for y, and we can do this using the approximations we see here and here. Well, if we use this first order approximation, y1, that's approximately y minus 1 plus 2h multiplied by dy over dx naught. So, knowing the value of dy over dx naught, that's 3, we have over here y minus 1 plus 2 multiplied by h, which is 0.1, multiplied by 3. So we have y minus 1 plus 0.6. Well, how does this help us? Well, the problem is so far we don't know what y minus 1 is. But if we go back to our second order approximation, what we can do is find another approximation for y1. So let's use this second order approximation. y1 is approximately 2y0 minus y minus 1 plus h squared lots of d squared y over dx squared naught. So we have over here 2 times by 0 minus y minus 1 plus 0.1 squared lots of d squared y over dx squared naught, which we found to be minus 1. And therefore, if we tidy this up, we would have y minus 1 and then the negative of that minus 0.01. So far we have y1 being approximately equal to y minus 1 plus 0.6, and we also have y1 being approximately equal to minus y minus 1 minus 0.01. So what we can do is, well, if I call this 1 and if I call this 2, we can add together 1 and 2. And if we do that, we've got y1 plus another y1, so that's 2y1. And then we've got y minus 1 minus y minus 1, well that's 0 y minus 1. And then we've got 0.6 minus 0.01. So in other words, we've got 2y1 being approximately 0.59, and therefore y1 is approximately 0.295. And now what we can do is use our differential equation to find out what d squared y over dx squared 1 is. So d squared y over dx squared 1, that will be equal to 2 lots of y1 squared minus x1 minus 1. So we've got 2 lots of 0.295 minus x1, which you'd remember is 0.1, and then we've got minus 1. So it turns out over here we get minus 0.92595. So now that we've completed our first iteration, we can now find out an approximation for y at x equals 0.2. So let's carry out our second iteration. So x2, that will of course be equal to 0.2. And with this, we can find out the estimate for y2. So to do this, what we can do is use the second order approximation as we see here. So y2, this is approximately 2 lots of y1 minus y0 plus h squared lots of d squared y over dx squared 1. So we have 2 lots of y1, which we found to be 0.295. So we've got 2 lots of 0.295. Then we've got minus y0, which was 0, plus h squared, so we've got plus 0.1 squared, lots of the second derivative 1, which is this value here of minus 0.92595. So therefore, what we'd have is 0.5807405, which, if you want, you can round to 3 significant figures. We end up with 0.581 to 3 significant figures. Question number 2. We have to use algebra to determine the values of x for which x plus 1 over 2x squared plus 5x minus 3 is greater than x over 4x squared minus 1. And before we do anything else, I think it might be a good idea to factorize the denominator here and factorize the denominator here. So if we do that, we will end up with x plus 1 over 2x minus 1 lots of x plus 3 being greater than x over 2x minus 1 lots of 2x plus 1. Now let's take everything over to one side, and in doing so, what we will have is this, the x plus 1 over 2x minus 1 lots of x plus 3 minus this, the x over 2x minus 1 lots of 2x plus 1 being greater than 0. Now, to make things a bit easier, what we can do is ensure the denominators are the same. So if we consider this term, and if we want the denominators to be the same, well, what I want on the bottom here is 2x minus 1 lots of x plus 3 lots of 2x plus 1. And on the top, well, we still have the x plus 1. And of course, because we've got a 2x plus 1 here, we would also need a 2x plus 1 here. It's as though these cancel out, leaving us with this. And similarly, if we want the denominators to be the same, well, here we'd end up with 2x minus 1 lots of 2x plus 1, and then we have x plus 3, and then on the top we still have this x, and then we have the x plus 3 here too. It's as though the x plus 3's cancel out, leaving us with this result here. And of course, all of this is greater than 0. And now we have a common denominator of 2x minus 1 lots of x plus 3 lots of 2x plus 1. And on the top, what we have is x plus 1 lots of 2x plus 1 minus x lots of x plus 3. And all of this is greater than 0. So what we'd do now is simplify the top. So if we expand along the top, we have x lots of 2x, well, that's 2x squared. And then we've got x lots of 1, which is x, and then we've got 1 lots of 2x. So in total, we'd have 3x. And then we've got 1 lots of 1, which is 1. And then we've got minus x times by x, which is x squared. And then we've got minus x times by 3, so we've got minus 3x. And on the bottom, we have 2x minus 1 lots of x plus 3 lots of 2x plus 1. And all of this is greater than 0. So on the top, if we tidy all of this up, we've got 2x squared minus x squared. Well, that will be 1x squared. And then we've got 3x minus 3x, that's 0x, and then we've got the plus 1. And the bottom would remain the same. on the bottom we'd still have 2x minus 1, lots of x plus 3, lots of 2x plus 1. And this, of course, is greater than 0. And if we take a look at the denominators, what we can do is state the critical values. For the critical values, we have x equals minus 3, x equals minus 1/2, and x equals 1/2. Now, what we can do is test values about these critical values, and from that we can find our solution. So here I recommend creating a quick diagram showing the critical values, and we will test values about each of these critical values. So for example, if we choose something which is less than minus 3, for example minus 3.5, well, on your calculator, if we type in minus 3.5 and store this into our calculator under the answer function, well, we'd have answer squared plus 1 over 2 lots of answer minus 1, lots of answer plus 3, lots of 2 answer plus 1. And it turns out here we get a value which is negative. So we have here a negative value. And if we test a value which is in between minus 3 and minus 1/2, for example minus 2, well, what we'd have here is minus 2 squared plus 1 over 2 lots of minus 2 minus 1, lots of minus 2 plus 3, lots of 2 lots of minus 2 plus 1. It turns out here we get a value which is positive. And if we test a value in between minus 1/2 and 1/2, for example 0, well, what we'd have then is 0 squared plus 1 over, well, here we've got 0 minus 1, lots of 0 plus 3, lots of 0 plus 1. It turns out here we get a negative value. And if we test a value greater than 1/2, for example 1, well, we'd have 1 squared plus 1 over 2 minus 1, lots of 1 plus 3, lots of 2 plus 1. So it turns out here we get a value which is positive. So we are looking where the inequality is greater than 0, and it's greater than 0 here and here. And don't forget, these values will extend off to infinity and negative infinity. So with that, what we can conclude is our solution to this inequality in set notation, well, we'll have x belonging to a set of real numbers where x is in between minus 3 and 1/2, or x belonging to a set of real numbers where x is greater then 1/2. Question number 3. For the first part, we have to use the substitution t equals tan of x upon 2 to prove that cot x plus tan of x upon 2 equals cosec x, where x doesn't equal some multiple of pi. And of course here n would represent a set of numbers which are integers. So, for the first part, well, if we have t equals tan of x upon 2, then sin x, this will equal 2t over 1 plus t squared. Cos x, that will equal 1 minus t squared over 1 plus t squared, and tan x, that will equal 2t over 1 minus t squared. And if we take a look at what we have on the left hand side, we have cot x plus tan of x upon 2. So if we begin with the left hand side, we have so far cot x plus tan of x upon 2, and of course recognizing that cot is the same as 1 over tan, we would have 1 over tan, so 1 over 2t over 1 minus t squared. In other words, we'd have the reciprocal of this, 1 minus t squared over 2t, plus tan of x upon 2, which is just t. And if we write this t with a denominator of 2t, well, what we'd have is 1 minus t squared over 2t plus 2t squared over 2t. And of course, the 2 divided by 2 gives 1, and t squared over t gives 1t, as we have here. And now that we've got a common denominator, we can combine these, so we would have 1 minus t squared plus 2t squared over 2t. In other words, we'd have 1 plus t squared over 2t, and if you notice, this result is the reciprocal of this result, and therefore here what we have is 1 over sin x, which is the same as cosec x, and that's what we wanted to show. For the next part, an engineer models the vertical height above the ground of the tip of one blade of a wind turbine shown in figure 1. The ground is assumed to be horizontal. The vertical height of the tip of the blade above the ground, h meters, at time x seconds after the wind turbine has reached its constant operating speed, is modelled by the equation h equals 90 minus 30 lots of cos of 120x degrees minus 40 lots of sine of 120x degrees. And part A, we have to show that h equals 60 when x equals 0. So, for the part A, well, if x is equal to 0, then we have h equals, well, we'd have 90 minus 30 lots of cos of 0 minus 40 lots of sine of 0. So we have h equals 90 minus 30 times by the cosine of 0 minus 40 times by the sine of 0. So we have 90 minus 30 minus 0, which is just 60. So when x is 0, h is 60. Now, for part B, using the substitution t equals tan of 60 x degrees, we have to show that this equation here can be written as h equals 120t squared minus 80t plus 60 over 1 plus t squared. So, for part B of the question, if t is equal to the tan of 60x degrees, then using the t formula, sine of 120x degrees is equal to 2t over 1 plus t squared. Cos of 120x degrees is equal to 1 minus t squared over 1 plus t squared, and tan of 120x degrees, that will equal 2t over 1 minus t squared. So, we know already that h is equal to 90 minus 30 times by the cosine of 120x degrees minus 40 lots of the sine of 120x degrees. So now what we can do is use the t formula as we see here. So we've got h equals 90 minus 30 lots of this result here, and then we've got minus 40 lots of this result here. So, what we can now do is write everything so we've got a common denominator of 1 plus t squared. And if we do that, well, we'd have 90 lots of 1 plus t squared over 1 plus t squared, and then the rest of the results as we see here would remain the same. So we've got 90 lots of 1 plus t squared over 1 plus t squared minus 30 lots of 1 minus t squared over 1 plus t squared minus 40 lots of 2t over 1 plus t squared. And therefore, on the top we can tidy all of this up as 90 lots of 1 plus t squared minus 30 lots of 1 minus t squared minus 40 lots of 2t, and on the bottom we would have 1 plus t squared. So if we expand along the top, we have 90 plus 90 t squared, and then we've got minus 30 plus 30 t squared, and then we've got minus 80 t. And along the bottom, we would have 1 plus t squared. And if we tidy this up even further, well, we have 90t squared plus 30t squared, so that will be 120t squared, and then we've got minus 80t, and then we've got 90 minus 30, which is 60. And on the bottom, what we have is 1 plus t squared. So therefore, h is equal to 120t squared minus 80t plus 60 over 1 plus t squared. This is the result which we wanted to show. And then for part C, hence find according to the model the value of x when the tip of the blade is 100 meters above the ground for the first time after the wind turbine has reached its constant operating speed. And therefore what we need to do here is set h equal to 100 meters. So for part C, we have 100 equals this over here. So we've got 100 equals 120t squared minus 80t plus 60 over 1 plus t squared. And if we multiply through by 1 plus t squared, well, here we'd have 120t squared minus 80t plus 60 equals 100 plus 100 t squared. So if we simplify this, we would have 20t squared minus 80t minus 40 equals 0. And if we solve this for the values of t, well, let's use our calculator. We have 20t squared minus 80t minus 40. So t is equal to 2 plus minus root 6. Now, if you recall, we know already t is equal to the tangent of 60x. So we have tan of 60x degrees equals 2 plus minus root 6. So if we find out the values of 60x, well, we have the inverse tangent of 2 minus root 6, and then if I add on 180, it turns out here we get 155.79, etc. And then of course, if we store this into b, we'd divide this by 60 later on. And then also we've got the inverse tangent of 2 plus root 6, which is 77.33, etc. So dividing these by 60, we end up with x equaling 1.28, etc. And then we've got the other value divided by 60, which is 2.59, etc. And if you recall from the question, we are looking for the first time after the wind turbine has reached its constant operating speed, and therefore we'd have to take the first solution. So we have x equals 1.28, rather 1.29, to three significant figures, and this over here corresponds to the first time. Question number 4. Figure 2 shows a sketch of the parabola C with equation y squared equals 4ax, where a is a positive constant, and the point S is the focus of C, and the point P has coordinates ap squared, 2ap, and this lies on C, where P is greater than 0. And part A, we have to write down the coordinates of S. Well, clearly, S is our focus, and that would have coordinates A, 0. So let's add this to the diagram. S has coordinates A, 0. And then for part B, we have to write down the length of SP in terms of A and P. Well, let's add on the coordinates of P. We've got A, P squared, and 2AP. Well, first of all, we need to recognize that the equation of the directrix, well, if we first of all show the directrix, the equation of the directrix is given by x equals minus a. And then what we also need to recognize is that the distance from S to P is the same as the distance from P to the directrix, as we see here. So this is equivalent to this length. And if we call this point D, for example, then what we can do is find out what dP is, and then from that we can conclude what SP is. So, for part B, if we were to find out what dP is, well, to go from D to P, we have here, from D to the y-axis, a length of A, and from the y-axis to P, we've got a length of AP squared. So the total length will be given by A plus AP squared. So that's what dP is. And therefore, as over here, SP equals dP, we can therefore conclude that SP has a length of A plus AP squared, and we could have found that out through Pythagoras as well, but that would have been far more complicated. Now, for part C, the point Q with coordinates AQ squared to AQ, where P doesn't equal Q, also lies on C, and the point M is the midpoint of PQ. We're given that PQ is equal to -1, and we have to prove that as P varies, the locus of M has equation y squared equals 2a lots of x minus a. So, first of all, let's add on some point q. So if we add on some point q, let's say here, well, q has coordinates aq squared 2aq, and the midpoint of pq, well, first of all, let's add on the line pq that's shown over here. M would be the midpoint of this, which will lie over here somewhere. So here we've got point M. Now we can find out the coordinates of M by finding the averages of the x coordinates and then the average of the y coordinates. So first of all, for part C, M, this has coordinates ap squared plus aq squared over 2, and then we have 2ap plus 2aq over 2. And therefore, if we simplify this, you can see therefore in conclusion, M has coordinates a lots of p squared plus q squared over 2, and then we have a lots of p plus q. So if we add those coordinates to our diagram, well, M, we have here a over 2 lots of p squared plus q squared, and we've got a lots of p plus q. Now, the idea is, in this question, we have to show that as p moves around, the locus of M would have this equation here. Now, what we can do over here is, first of all, say that, well, what we'll do is we'll say, let M be x, y. Okay? So what we're saying over here, M has general coordinates x, y. In other words, what we're saying here is x is equal to a lots of p squared plus q squared over 2, and y is equal to a lots of p plus q. Now, what we can do here is, first of all, define what p squared plus q squared is, and you'll see why I'm doing that. So if we make a side note, p squared plus q squared, this will equal, well, what we can do actually is find out what p plus q all squared is. This will equal p squared plus 2pq plus q squared, and therefore p squared plus q squared, this will equal p plus q all squared minus 2pq. And we know what pq is. We were told that's -1. So p squared plus q squared is equal to p plus q all squared minus 2 lots of negative 1. So we end up with p plus q all squared plus 2. Now you'll find over here we've got a p plus q, and here we've got a p plus q. So what we can do is from here rearrange to find out what p plus q is. So what we also know is p plus q is equal to y over a, and therefore what we can conclude is p squared plus q squared is equal to y over a squared plus 2. How does this help us? Well, if we take a look at the x coordinate, well, so far we have a lots of p squared plus q squared over 2. So we have x equals a lots of p squared plus q squared, which is this result here. So perhaps if we rewrite this as x over 2 multiplied by y over a all squared plus 2, that might make things a bit easier for us. So this result inside this curly bracket is what p squared plus q squared is. And now we need to tidy this result up to show this result here. So we have x equals a over 2 lots of y squared over a squared plus 2, and if we expand the a over 2 into the bracket, we'd have x equals, well, we've got a y squared over 2a squared, so here we'd end up with y squared over 2a. And then we've got a over 2 times by 2, which is just a. And then if we rewrite the a, so we've got a denominator of 2a, we have x equals y squared over 2a plus 2a squared over 2a. So we have x equals y squared plus 2a squared over 2a. And if we multiply through by 2a, we have 2xa equals y squared plus 2a squared. So we've got y squared equals 2xa minus 2a squared, and if we factorize out the 2a, we can therefore conclude y squared is equal to 2a lots of x minus a. And that's exactly what we wanted to show. Question number 5. Figure 3 shows a solid display stand with parallel triangular faces ABC and DEF. And triangle DEF is similar to triangle ABC. And with respect to a fixed origin, the point A has coordinates 3, minus 3, 1. The point B has coordinates minus 5, 3, 3, and the point C has coordinates 1, 7, 5. The point D has coordinates 2, minus 1, 8. The point A has coordinates minus 2, 2, 9. And the point F has coordinate 1, 4, 10. The units are in centimeters, and part A we have to show that the area of the triangular face DEF is 1/2 lots of the square root of 339. So, to do this, well, what we need is the vector DE and also the vector DF, and then we can use a standard formula to work out the area of this particular triangle. So for part A, if we first of all find the vector DE, well, the vector DE, we have the vector OE, which is minus 2 I plus 2j plus 9k, and then we subtract off the vector OD, which is 2i minus j plus 8k. And if we work this out, we get minus 4i plus 3j plus k. And for DF, we have the vector OF, which is I plus 4j plus 10k. And then we have OD, which is 2i minus j plus 8k. So if we work out the vector DF, we have minus I plus 5j plus 2k. How does this help us? Well, what we can now do is find out the area of the triangle DEF. So therefore, the area of the triangle DEF, this is equal to 1/2 times the mod of DE multiplied by DF. So we need to cross this vector with this vector here. So we have 1/2 lots of the mod of DE, which is this over here, cross with DF, which is this over here. Okay, so if we work this out, well, what we can do is work this out on our calculator. So we've got 1/2 lots of the mod of, well, all we have to do here is, if we go to the vector submenu and define both of these vectors, well, we have here minus 4, 3, 1. And then here, if we define that vector, we have minus 1, 5, 2. And then if we cross those vectors, what we'd end up with is I plus 7j minus 17k. So we would have here 1/2 multiplied by 1 squared plus 7 squared plus minus 17 squared square rooted. What we'd end up with is 1/2 times by the square root of 339. Now for part B, we have to find in centimeters cubed the exact value of the display stand. Well, to do this, what we need to do is recognize we would have had a larger triangular prism take away a smaller triangular prism. And so you can see that here we've got a smaller triangular prism and a larger triangular prism. And what we can do, well, if we call this line L1, and if we call this line L2, if we find the intersection of L1 and L2, let's call it T, for example, then what that will allow us to do is find out the volume of this first triangular prism and the larger second triangular prism, and subtracting the results will give the required volume. So for us to find out what L1 and L2 are, well, we need a direction vector for L1 and we need a direction vector for L2. And for that, what we can do is find the vector AD and also find the vector CF. Those will be the direction vectors of L1 and L2 respectively. So for part B, we have AD, which is equal to 2i minus j plus 8k minus 3i minus 3j plus k. So I'm just using the coordinates of A and D to work out the vector AD. So the vector AD is equal to minus I plus 2j plus 7k. And CF, that's equal to minus I plus 4j plus 10k minus I plus 7j plus 5k. And it turns out here we get 0i minus 3j plus 5k. How does this help us? Well, what we can now do is, knowing that L1 would pass through the point D and L2 passing through the point F, we can therefore conclude from here that L1, that has vector line equation R equals 2 minus 1, 8 as a column vector, plus lambda, lots of the direction vector, minus 1, 2, 7. And similarly, the line L2, that has equation R equals 1, 4, 10, plus mu lots of 0, minus 3, 5. And now what we can do is solve these two lines simultaneously to find out the coordinates of T over here. So, in other words, we have 2 minus lambda minus 1 plus 2 lambda, 8 plus 7 lambda equals 1, 4, 10 plus 0 lambda, and here we've got minus, rather 0 mu, minus 3 mu, and here we've got 5 mu. So if we, well, on the top we would have 2 minus lambda equals 1, and therefore lambda is equal to 1. Now, we have to think to ourselves if it would be worth our time calculating what mu is. Well, it wouldn't, because the value of lambda here would suffice to help us find out the coordinates of t, because all we have to do is substitute this in to this line here. And if we do that, we can therefore conclude that t, this would have coordinates 2, minus 1, minus 1, plus 2 lots of 1, and 8 plus 7 lots of 1. So therefore, coordinates of t will be 1, 1, 15. So let's add this to the diagram. We have 1, 1, 15. So how does this help us? Well, what we can do is find the volume of the larger triangular prism. We need to find out what AT is, what AB is, and what AC is. So, if we first of all find out what the vector AT is, the vector AT is equal to I plus 15j minus the vector A, which is 3I minus 3j plus k. So if we work this out, we have minus 2I plus 4j plus 14k. What we can also do is find out the vector AB. So for the vector AB, we have minus 5I plus 3j plus 3k minus 3I minus 3j plus k. So if we work this out, we have over here minus 8I, and then we've got over here 3 minus 3, so that will be 6j, and then we've got 3 minus 1, so here we'd end up with 2k. And then the vector AC, well, the vector AC is equal to vector C, which is I plus 7j plus 5k minus the vector A, so we subtract off 3I minus 3j plus k. So if we work this out, we have 1 minus 3, which is minus 2. Then we have 7 minus 3, so that's 7 plus 3, which is 10. And then we've got 5 minus 1, which is 4. So now that we know what AT, AB, and AC are, we can now find out the larger volume. So, to find out the larger volume, so let's just write this on the large volume, we would have 1/6 lots of the mod of AT dot product with AB cross with AC. So we've got 1/6 lots of, well, 80, that's this over here. And what we need to do is dot this with AB cross with AC, which is this over here. So if we work all of this out, we would have 1/6 lots of the mod of this vector here, dot with, well, if we work out that cross product, we can do this on our calculator. So if we define vector A, we have here -8. Of course, here we've got 6j plus 6j plus 2k. And then if we define this vector, we have this vector. So let's define that in B. This vector, which is -2, 10, and 4. And then let's also define this vector to be -2, 4, and 14. So we've got we've got A cross with B. So here we've got this cross with this. So we've got this vector dot with 4i plus 28j minus 68k. And what we'll do is we'll find the dot product of, rather here we've got C dot product with that. So here we get -848. So we've got 1/6 lots of the mod of -848. So it turns out here we would have 424/3 centimeters cubed for the large. Now, to find out the volume of the smaller shape, what we'd need is, first of all, the vector dt. So if we find out the vector dt, that's equal to I plus j plus 15k minus 2i minus j plus 8k. So if we work this out, we end up with -i plus 2j plus 7k. So that's what dt is. And we can also find out what dE is. Well, we already worked it out over here. And we also worked out what dF is. So that'll be quite useful for us. So let's just paste that over here. Let's just move this down to the next line here. So now what we can do is find out the small volume. So if we find out the small volume, what we would have here is 1/6 lots of the mod of dt dot width de cross width df. So we've got 1/6 lots of the mod of dt, which is this over here. So this is what dt is, and then we dot this with the cross product of de and df. So we've got this over here, and then we cross this with this vector here. So if we work all of this out, well, this cross this we already worked out previously. So we've got over here a 6 lots of minus I plus 2j plus 7k dot with the result of these two crossed together, which we worked out over here. So if I just paste this over here, we worked a lot of these quantities out before, happily for us. So if we work all of this out, we've got a 6 lots of the mod of, well, all we have to do here is just use our calculator. So if we define vector A, we have here minus I 2j 7k, and if we define the other vector, we've got I plus 7 minus 17. So if I dot product those together, what we'd end up with is the mod of minus 106 multiplied by a 6th. So here we get 53/3 centimeters cubed, and therefore the volume of the display stand would have 424/3 minus 53/3, and working this out we get 371/3 centimeters cubed.